students, it's time for this new video. We're going to look at infinite series and sequences of partial sums. So it's continuing the conversation about sequences, but now we're going to start adding up those terms in the sequences. Let's go ahead and take a look here. Okay, first of all, what is an infinite series? Has this form as we see right here. That is the summation. Start our index k at 1, and we're going to add up all the ace of k's all the way to infinity for k. That just means, in the notation, in case you forgot, k is 1, you get a 1, then you add it to when k is 2, you get a 2, then you add to when k is 3, you get a 3, and just keep adding them. So we're going to let our index change from 1 to infinity, and whatever these expressions are, ace of k's, just keep adding them up forever. Very similar to notation for sequences. Only difference now is we're adding up the terms rather than just listing them. So for example, just to see a series, here is series, k is 1 to infinity of 1 over k. So you just think, okay, if k is 1, you get 1 over 1, which is 1. Then I'm going to add that to when k is 2, you get 1 over 2. So 1 plus a half. Then when k is 3, you get 1/3. Add that to the previous amount. K is 4, you get a 4th, and you just keep adding these up forever. It's actually a special series we call the harmonic series. We'll look at this more in depth in a video in the future, but just an example just to see a series, right? Add up all that stuff forever. Now, question really is, can an infinite series converge? And so probably, right, you'd think, because otherwise if they always diverge, we wouldn't talk about them. But it is a strange concept. And that is, can we add up an infinite amount of finite valued numbers and get another finite number? That's what this conversation is. So we're going to kind of see how this would work, how it's feasible to get a finite number by adding up infinitely many other finite numbers, by considering what we call the unit square. And that's just a square with side lengths 1. Haha, little typo there. That's th, obviously. So here's the unit square, and just side length 1, side length 1. And clearly we know this square has an area of 1 square unit. 1 times 1 is 1. All right, but we're going to add up pieces of areas of the square to get the actual area of the square, utilizing the concept of an infinite series. So let's take a look here how this is going to happen. How are we going to do this? We're going to find the area of this unit square by kind of piece by piece, as we're going to see. We're going to start by first chopping the square into 2 pieces. And when I say 2 pieces, 2 equal pieces. So we'll just chop it right down the middle and get a picture that looks like so. And you say, okay, well, the area of half of that square is, well, half the area of the square, which should be a half, right? Because the area is 1. Let's just call that value S1. And like we said, that area is a half. Now, clearly, that is not the area of the square, but it's half the area of the square. And what we're going to do next is add up more pieces of areas to the previous amount. So what if I then took half of the remaining half, that white region, and add that area to the previous area? So we would get a picture that looks like so. So I took half of the remaining part, that purple shaded region, that has some area, and we're going to add it to the previous shaded region, that blue region, and then we get closer to the actual true area of the square. The area of the purple region is 1/4, and so if I add that to the previous amount, that S1 as we called it, then I got a half plus a 4th, and that ends up being 3/4. So the total shaded region right now is 3/4, and we're going to call that S2. What if we keep doing this? Let's then continue this process, take half of the remaining non-shaded region, and add that to the previous amount of area. So we do it again in this picture. Okay, so I take half of the remaining non-shaded region, kind of that yellowish looking color there, and I'm going to add that to the previous total amount. The area of that yellowish region is an 8. That purple region, remember, was a 1/4, and then the blue region was a 1/2. When we added up a 1/2 and a 1/4, we called that S2. So now I add that result S2 to this new shaded region, 1/8, and get, as we're going to say, S3. So that's a 1/2 plus a 1/4 plus an 1/8. That gives us a total of 7/8. So we're getting closer to the true area of the square. And we're going to keep doing this. Do it one more time before we generalize. And I take 1/2 of the remaining part, that pinkish region right there. So remember, we got a 1/2 in the blue, a 1/4 in the purple, an 1/8 in the yellow, and now this pinkish looking region, that's going to be 1/16. So I'm going to take the 1/16 and add it to the S3, which we found was 7/8. We're going to call that S4, and that's what we see right here. Add the 1/16 to the previous amount, S3, and I get 15/16. Getting closer to the true area of the square. And let's just say we keep doing this. Say we did this n times. Then we're going to get a picture that looks something like this. And you just keep going and 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 going. And so if we kept doing that, adding a little 1/2 of the remaining part, 1/2 of the remaining part, and so on to the previous amount of area, we would eventually get very, very close to the true area of the square. So if we do this, notice the pattern here. Each time we're adding another power of 1/2. And so in general, if we did this n times, that last piece that we're adding, that little piece of area, would be adding 1/2 to the n to the previous total amount. And in general, we should also be hypothesizing here that this area is 2 to the n minus 1/2 to the n. You might be wondering where that's coming from. Notice in the previous sums that we found, each denominator was 2 to the n, like here in S4, right? That was 15/2 to the 4th power. And then 15 is 1 less than that, right? So it's the same as saying 2 to the 4th minus 1/2 to the 4th. And then when we had S3, similar. Remember, this was the same as 7/2 cubed, which is the same as 2 cubed minus 1/2 cubed. So this happens each time. That's where this formula down here is coming from. That is 2 to the n minus 1/2 to the n. And then you think, well, what if we then let n become infinite? Just let it become infinitely large. Do this as many times as possible. In other words, take the limit of these sums as n goes to infinity. Then it would be equal to 1. And of course, 1 is the actual value of the area of the unit square. And so as we see, we're adding up infinitely many pieces to get a finite amount of stuff. So, you know, it's just an example exploring this idea. Okay, and actually what we did in this example, we may not know it yet, but we're about to. We used what's called partial sums. So we're going to have to explore what this means. The concept of a partial sum is very crucial to understanding whether or not an infinite series converges or not. So in general, here's how we're going to describe infinite series. Say we have a sequence now. So just a list of some numbers that we've seen so far that's infinite, right? A1, A2, A3, and so on and so on and so on forever. Sequence of A sub k's. Then what we want to do is add up these terms, A sub k's, and we get the sum of all the A sub k's is equal to the infinite series. Does this equal a finite number or does it not? That's the question, depending on what A sub k is. We say that the sequence of partial sums, the sequence of S of n's, if you will, these are very similar to what we saw in the unit square computation. This is really telling us what our sum is if we added up the first n terms of the sequence. So what does this sequence actually have as its terms? Well, the first term would just be the very first term of the sequence itself. So I haven't added anything, I just took the first term. So we call that S1. Then we're going to add the first two terms. That new term, which we'll call S2, is A1 plus A2. The third term in the sequence of partial sums, S3, would be take the previous amount, A1 plus A2, and then add A3 to it. And then S4, right, the fourth term in the sequence of partial sums is going to be the sum of the first four terms. And in general, the nth term in this sequence of partial sums is take the previous sum, S of n minus 1, and then add the next term in the sequence to it, A sub n. So that's just the sum of the first n terms. This itself is a sequence. And if we let n now go to infinity, then what we're really saying is, oh, that is really just the entire sum of the infinite series. We're adding up all infinitely many terms in the sequence. So you may suspect that if this sequence itself, this list now, which is listing out the sum of the first term, the sum of the first two terms, the sum of the first three terms, and so on and so on and so on, the sum of the first n terms, and we just did that forever, that sequence should converge if the series converges and vice versa. And that's what this is saying. If the sequence of partial sums, here, has a limit, you look at the limit of that sequence, let's say it's a real number L, then the infinite series, sum of all the a sub k's, converges, and we're going to write that the series itself, series of a sub k's, is the same as taking the limit as n goes to infinity of adding up the first n terms, which is just the same thing as saying the limit as n goes to infinity of the nth partial sum, and that, if it's converging, equals L. So really, the limit of the sequence of partial sums is the same thing as the infinite series itself. However, if that sequence of partial sums diverges, then the series diverges as well. So we want to know how a series is behaving. We look at its sequence of partial sums in its most fundamental form, and however that sequence behaves, that's how the infinite series behaves. We're going to look at an example here to kind of, get a better idea of how this is working. And we're going to consider the series here, this infinite series, the series of 3 over 4 to the k is 1 to infinity. Okay. So first thing we're going to do is just find the first four terms of the sequence of partial sums, get an idea of how that works. So we just start when k is 1. When k is 1, we get that S1, which is just the same as the very first term, A1, is just 3/4. Now, when k is 2, we get S2, which is the same as taking the previous amount, S1, and adding it to the next term in the sequence, A2. What's that going to be? That's going to be 3/4, right, plus 3 over 4 squared. And if we added that up, that ends up being 15 over 16. So those are the first two terms in the sequence of partial sums. How about when k is 3? Then S3 is going to be S2 plus the third term, A3, which is 15 over 16, as we found, that was S2, and then plus the next term, 3 over 4 cubed now. If we add that up, that would be 63 over 64. And then finally, when k is 4, we get that the fourth partial sum, S4, that's the previous partial sum, S3, plus the next term, A4, which is 63 over 64. That's our S3. And then plus now the fourth term, which is 3 over 4 to the 4th power. And if we add that up, that would be 255 over 256. So the first 4 terms in the sequence of partial sums, if we're looking at here the sequence of partial sums, this is going to be 3/4, 15/16, 63 over 64, 255 over 256, and so on and so on. The first 4 terms in the sequence of partial sums. Now, does the value of this series exist? Well, if so, then the series, right, k is 1 to infinity of 3 over 4 to the k should be equal to the limit as n goes to infinity of s of n, that sequence. So we're going to have to figure out a formula for this explicit nth term in the sequence of partial sums. And you may notice, very similar to that unit square problem, this is really the same as the limit as n goes to infinity of that nth term is. Notice each numerator there in our partial sum terms is 1 less than the denominator, and the denominator is just a power of 4. So that is just going to be the same thing as saying take to the denominator, 4 to the n, subtract 1 from it, and then divide that by 4 to the n. That limit has a value of, you guessed it, 1. So it converges. And we just showed an example of how to use this sequence of partial sums to get the value of a series. Sometimes we can do this without a problem. Other times it's very difficult to do. So there's a long conversation ahead about all the different types of series we see and how we go about figuring out whether they converge or not. So there's your introduction to infinite series, which involves the real important concept of the sequence of partial sums. And then from here, we're going to keep talking about more properties of sequences and whatnot so we get a better grip on whether or not we have a sequence or hence a series if we're looking at the sequence of partial sums, whether or not those converge or diverge. So that's it for the video. Hope it helped. And until next time, see ya.